Illustration helps to sort of highlight what I just mentioned. So this representation at the bottom is basically the frequency of action potentials. So in the middle, the muscle is nice and relaxed, and basically the action potential firing rate is standard, it's set. Now, when we stretch that muscle, right, think about the example that I gave with the patella tendon reflex. Basically, we speed up the action potential frequency or the firing rate, and that sends a signal which causes the muscle to contract. Alternatively, if the muscle is contracted, we decrease that signal by simply decreasing the action potential firing, and so we do not elicit that reflex. Right? Now, there's one thing we want to bear in mind as we talk about the speed of this reflex, or the speed of the action that's associated with this reflex. Now, alpha motor neurons and gamma motor neurons typically conduct their action potentials at a different rate. Alpha motor neurons are heavily myelinated, and so they have a faster rate of conduction. Okay, and so when we elicit this reflex, the alpha motor neuron, which innervates which part of the fiber? Anyone remember? We just talked about it. What part of the fiber does the alpha motor neuron innervate? Is it the extrafusal or the intrafusal? The extrafusal. So basically, the alpha motor neuron, which innervates the extrafusal fiber, will typically respond faster than the gamma motor neuron. And so what we have is the extrafusal fibers contracting first. And in this top image, we can see that the muscle spindle has now gone loose, sort of bubbly here. This is because the gamma motor neuron is conducting its action potentials much slower. And so the response has not gotten to this part of the muscle yet. All right. Now in the bottom, what we can see is that when the gamma motor neuron finally catches up, this readjusts the spindle. So now it's nice and taut. Right? It readjusts the spindle, and this is very important because it needs to be readjusted so it can continue to detect any further changes in the length of the muscle. Alrighty? So you just want to bear that in mind, that the alpha motor neuron, more myelinated, faster conduction velocity, is going to respond first, contracting the extrafusal fibers, right? And there's going to be a short time where the extrafusal fibers have contracted, but the intrafusal fibers have not. Now, finally, when they catch up with each other, we have that muscle spindle stretching out, becoming more taut, and spindle can continue to pick up any other changes in the length of that muscle. All righty. Any questions on the muscle spindle? Now, the second receptor we're going to talk about is called the Golgi tendon organ. This one is not as complicated. It's associated with one type of sensory nerve ending, that's your 1 degree afferent fiber. And the function of the Golgi tendon organ is to detect any tension, excess force in the tendon. Okay? Now, unlike the muscle spindle, the GTO is found within the tendon itself and not in the muscle belly. And it's basically protecting the tendon from being ripped, from being torn, from being overexerted or damaged because of excess load. And so what happens is, let's say you're picking up a load that's too heavy, the tendon will pick up that excess tension that's being put on it, and it will send a signal, right, that same frequency coding signal to the central nervous system via type 1B afferent fibers, which results in a reflex inhibition of this muscle. Okay, that makes sense. If you're lifting a load that's too heavy, you rupturing or injuring this tendon, immediately the muscle is going to send a signal, or the tendon rather is going to send a signal to the spinal cord, which reflex inhibits, right? As a reflex is going to inhibit the contraction of this muscle and stop that overexertion. Okay, so in this way, the GTO is also very protective of the tendon and of the integrity of the muscle.